Fritz set me up. Well. Everybody hear me? So, I have a story to tell you as well. This is short, however. Year 2000, I was applying for graduate school. And among the various places I went to was the University of Texas at Austin. And I showed up in Professor Benedict's office, and he told me, you know, you should come here. We have a fantastic set of data. We are going to determine the masses of well-known planets all along with HST, FDS for the K to come. And I said, no, I want to discover new planets. Sorry, I'm going somewhere else. I want to see it.
Good choice.
Well, story number 2. Before we get into the this one. Before we get into the nitty-gritty of microsecond astrometry, let me give you one last fantastic success of millisecond astrometry in our own solar system. This is planet 9. Almost everyone has heard about it, I'm sure. This was recently by Caltech scientists, in fact, announced to be likely lurking in the 200 astronomical unit range in the far reaches of the solar system, most likely because it induces especially interesting perturbations on the orbits of trans-Neptunian objects, such as the very famous Sedna guy here. And so it should be there because it's perturbing trans-Neptunian objects. As of a couple of weeks ago, already people are beginning to question the idea of the fact that it may be there, maybe not. So will it last? We don't know. Certainly there are people out there who claim that this is more likely the case not to be true. We shall see. But now let's get to Gaia. This is going to be a lot of fun, and especially now almost 10 years into the run, yet another important sales pitch of what Gaia is going to do. Gaia is not doing it yet, but it's going to do it, trust me. Gaia is a global astrometry mission. It is a scanning satellite with operating space with a especially well-defined scanning law pattern. It uses 2 fields of view separated by what is called a basic angle of 106.5 degrees. And it measures positions along its sensitive direction, which is the along scan direction. It performs a very interesting pattern of observations throughout the terrestrial, and once every 6 months, it covers it all. Over the 5-year nominal mission lifetime, that's the observation pattern that you end up with using Gaia observation, which is highly non-uniform. There are regions in the sky that are actually very densely covered with a couple of hundred of observations over 5 years, and some regions are actually not very well covered, returning over of less than 50 observations. However, it is going to be a fantastic machine to improve by a couple of orders of magnitude the millisecond precision level, which has been set up as the standard by the PACOS mission and HST work, as shown by Fred. We are now in approximately 4 years of science operation. This is exact time since the beginning of science work. And we have collected an outstanding number of measurements. This is really big. The first element of the revolution, really the important element of the revolution, has happened just a couple of months ago. And this is the second data release of Gaia. There was the first one that happened in September 2016. That was already groundbreaking for some statistical aspects. But Gaia data release 2 really sets a change in the game. And this is a summary of the numbers you can bring home in terms of number of objects for which positions and brightness at the Gaia specific G band in photometry are observed. And obviously, the most important one is the larger than a billion data set of sources for which it was possible to measure proper motion apart, all the 5 basic astrometric parameters. In the era of Hipparchus, 20 years ago, you had of order of 100,000 stars for which you could measure these 5 numbers. This is the first fantastic revolution in the field provided by Gaia. This is an image. You will not be able to reproduce it easily with the Gaia data that are public, but it tells you what Gaia sees in terms of flux coming from our galaxy, the neighbors, and the local universe around. This is fantastic work. There are a couple of other things that I want to give out. You are welcome to look at movies and fantastic other interpretation images on the public Gaia website. The Hessel-Russell diagram that comes out with of order of 10 million stars for which you have very accurate parallaxes, for me is simply fantastic. Nothing ever has been done of this sort. And you can see the rotation of the Large Magellanic Cloud. This is a movie. This is just an instance. You can see the movie on the Gaia website. Nothing like this has been seen before. Fantastic. The focus of the talk is astrometry, so let's get to the nitty-gritty of it all. The typical way of assessing the performance of the instrument is looking at the precision with which astrometric parameters are measured. And this is the plot of the precision in the parallax as a function of the brightness of the source. This is for Gaia DR2, this is Gaia DR1, and this is what you expect to see at the end of the mission. The great news is that for relatively faint objects, say 14 or up to the faint end limit of the survey, we're already pretty close to what we expect for the end of the mission after just less than 2 years of observation. This is really surprising. There are a few issues. The 2 most important ones are the bright star regime. As you see, there is an arrow here that tells you that we are still a factor of several away from optimal performance. This is induced by the still not optimal calibration of the data in the bright star regime. There are several issues here that are listed. I will not get into the details of this. We can chat about it, get questions later on. At the very same end, there is a twist in what used to be a perfect straight line in the forecast for the loss of precision due to essentially domination by photon noise. And this is used to stray light that has become nuisance for the Gaia spacer. And this was entirely unexpected. We have to live with it. So there is a loss of performance for the data. So Gaia DR2 is the first element of the revolution. There are more to come. The pace at which we decided, the impact consortium, the data processing and analysis consortium of Gaia, has decided to publish data, release data for the community. Used to be on an approximately yearly basis. This has become too difficult to do because of really the very difficult task of putting together all the various pieces of the analysis and make them really fruitful and usable by the community. So we're now going on a 2-year basis, and the next data release will happen in 2020. And 2020, late 2020, is the first time in which there will be orbital solution published. Things are not stopping at the end of the nominal mission lifetime, which will be in just about a year from now. We got approved an extension until the end of 2020, and the European Space Agency is now working out the preliminary scientific approval for an extension of an additional 2 years. We hope to get finally double the mission lifetime and eventually reach a 10-year mission duration. So in the words of Virginia Trimble, couple of years ago at a youth symposium in Atlanta, Georgia. Well, Gaia also finds planets, right? We have seen all the fantastic stuff it does, HR diagram things. How do we find planets with Gaia? First, we have to take out slight nuisance, the fact that stars move on their own because of proper motion and parallax, and we have to first solve for the 5 basic astrometric parameters, and then eventually, in the residual through the observations, identify hints of orbital motion induced by companions, big and small. The task is accomplished in a not at all trivial way. I told you global astrometry is performed by Gaia in the sky. We're not looking at connecting differentially the motion of stars in small fields. We're looking at connecting stars observed at 150, 180, 90 degrees apart in the sky. And this way is implemented in a global astrometric solution that essentially solves for the 5 astrometric parameters plus spacecraft-related parameters plus calibration-related parameters plus error bar for all the stars observed by Gaia at once. And this is quite a task. It's of order of many billions of unknowns. But fortunately, as you have seen, we already reached a safe amount of redundancy with more than 100 billion observations. And once you have solved for your astrometric parameters, you are left with the task of seeing if there is actually hint of orbital motion. Let's take a look at the magnitude of the signal, and then we'll see what we are coming up against for Gaia. The amplitude of the signal is typically, we have seen it also in talk by Professor Benedict, typically a fraction of a milliarc second already looking at giant planetary companions in the vicinity of the star. And if you go down a mass, then you very soon hit the micro arc second regime. In this table, this is further illustrated. This is Jupiter, G-type star, 10 parsecs from the sun, half a milliarc second at 11 years of period. The Earth around the same star at the same distance in the habitable zone of its parent star will give you a fraction of a microsecond duration, amplitude of the signal. So the question is probably is not a question. This is not Gaia's thing to look for habitable Earth. But I'll come back to that in the one before the last slide. Now, we are coming up against a bunch of constraints that you have to deal with and modeling aspects that you have to be aware of. First of all is the limiting measurement precision of your instrument. Gaia has in the focal plane of the instrument a row of 9 CCDs, and this is the expected performance pre-launch of the way you can measure sufficiently accurately at the level of 50 or so microseconds the location of your source on a single CCD. This best case performance is in the bright star regime, where you are limited not by photon noise, but by calibration issues. The various elements in the orbit, in the error budget of your of the instrument assume photon noise, spacecraft aptitude calibration, and geometric calibration elements that should provide you approximately this floor. You sum up in a single transit 9 such measurements, and for the purpose of looking for planets in astrometry, you have a total transit measurement precision on the order of 20 microseconds in the bright star. Let's keep this number in mind because we'll come back to it. This is pre-launch with a caveat. We were expecting, and this was one of the most important worries for Gaia, an impact in the performance to be understood from the sun. We have solar panels that shade the spacecraft from the sun direct sunlight, but bombardment of heavy ions from the sun, especially because Gaia was launched essentially at the peak of the last solar cycle. We were expecting a significant impact in the astrometric precision of the order of maybe 10% or so, because of what is called charge transfer inefficiencies affecting the detectors that essentially distort the point spread function by bombarding each pixel of a CCD without allowing the modeling of a standard point spread function simply provided by your stellar source. This effect, as of today, is kept under control at a level that is still far from the impact we were expecting to see already in a couple of years into the mission. So this is actually a piece of very good news, because we got a bunch of other issues that we had to deal with that are making, for example, the quality of the calibration measurements of bright stars still very difficult. But this, which was expected to be really a big source of trouble, is not there. And so modeling aspects. General relativity kicks in for Gaia just as much as it kicks in for very high precision Doppler spectroscopy, and in a manner even more complicated. To go from pixel level coordinate measurements in the Gaia focal plane all the way to stellar positions in the barycentric celestial reference frame, there's a bunch of transformations here, half a dozen reference systems you have to move for. And in order to move from here to there, you really have to take into account in a fully relativistic manner the motion of the sources. And particularly the light path coming from the stellar source that is changed by gravitational light deflection when the star is seen close to the most important gravitational fields in the local solar system, the Sun, Jupiter, particularly. And also the effect, which is general relativistic in nature, induced by the motion of the observer with respect to the distant source, which is the aberration. All these effects at the tens of microsecond level precision do have an important impact. Once you've done your modeling right, what's left before you find planets is everything else, which is astrophysical in nature. Let's start with binaries. Binaries are sources of noise if you're looking for planets. Stellar binaries are plenty. We probably have 1 in 2 stars in the solar neighborhood being orbited by binary companions. And if you're looking for the wobble of your Jupiter-type object over here, this is the scale, over a time scale of several tens of years, you likely, in 1 in 2 times, might be having the signal superposed by a much larger signal, which is the one coming from a potential binary companion. Then on a time scale of 5 years, which is that of Gaia observation, might allow you to sample 1 full cycle of your Jupiter mass object, but also see your data affected by, depending on the object configuration, much larger drifts, linear or non-linear, induced by another companion. You have to deal with that. As much as you have to deal in principle with the nuisances coming from stellar activity. Very high precision Doppler spectroscopy sees this as hell for Gaia-like measurements, as you see in this table. This is much less of an issue, especially solar-type stars, even though they are extremely active, are not expected to impact Gaia astrometric measurements very, very significantly with the level of astrometric jitter. For Doppler spectroscopy, rotation is also a big issue. For positional measurement, this is not at all problem. At least this is out of the way. Gaia is very democratic, as I will show you in a minute. It observes stars of all types, of all ages, of all spectral types. It observes also young stars. If you're looking at stars that are very young, these might have disks, and additional sources of physical noises induced by a set of classes of effects, such as the ones that I am briefly listing here, can and might have, in fact, an impact in Gaia astrometry, whether the disks are marginally unstable, whether planets in cavities produce variable illumination in the disk, or whether inhomogeneities in different regions of the disk going around, and asymmetries of various types can be seen as astrometric effects in the Gaia data. We have no obvious understanding of how to deal with things such as these. We will see them as they come. Finally, before we get to see what Gaia can give you in the realm of exoplanets, how we are actually doing this in practice. In the plane of the sky, this is how the way you look for planetary orbital motion is seen. And this is essentially the modeling aspect of astrometric parameters plus planet parameters that is done, for example, in narrow-field astrometry. Gaia is intrinsically a one-dimensional scanning measurement. And in order to see this in the Gaia reference frame, you have to rotate by the scanning angle that will move at every observing date the so-called plane of the sky by an angle. This angle, the scanning angle, is the value that contains all the knowledge of measurement uncertainties that you have in the data. Your geometric calibration, your attitude modeling, general relativistic modeling, everything. It all sits here. If you get this wrong, you get the geometry wrong, and then your modeling ends up being much more complicated than you think. This is no trivial task. In the best case scenario, we have 12 parameters in the model. I'm talking about the model being the model, not everything, as Tom said at the beginning of this workshop. For us, this is just the model. 12 parameters minimum. If there are multiple planets, that can make 19, 20 something, etc., etc. So you have to deal with elements of sufficient redundancy in the data. After 2 years of observations, most stars, for example, only have of order of 25, 40, 50 observations. So the redundancy is still not very high. That's why also one of the reasons why orbit fitting algorithms have not been kicking in effectively yet. But there are a bunch of other issues that have been addressed at times by various speakers during this workshop. I'm not going into any details of this, but except for one, we need to make sure that we're getting things as right as possible. We have a reference sample of objects that are the known planet systems on a variety of detection techniques that we will have to probe the Gaia data against. But most importantly, we have to make sure that we are using as many algorithms as possible to see that we consistently provide results that make sense. And that's why in the direct processing analysis pipeline of that deals with orbit fitting, extrasolar planets are dealt with multiple algorithms for orbit fitting. Markov chain and genetic algorithms are the ones of choice that are being implemented. So then, what Gaia can give you? Gaia can give you many things. In my opinion, Gaia has an impact in the field of extrasolar planets that is extremely broad. Individually, it's not revolutionary. Seen as a whole, from a statistical point of view, at, let's say, low resolution, it is fantastic. And I'll try to give you a quick snippet of what Gaia can do for you in 3 classes, as a target selector, as a target characterizer, and as a planet finder. So TESS has just been launched, and it comes with a very nice input catalog that is essentially based entirely on the output of Gaia Data Release 2. The fundamental contribution of Gaia to transit space missions such as TESS and also PLATO later on down the line, is the possibility of selecting an input list of targets that is completely clean of unwanted stellar types, such as giants, or most importantly, giants. In a recent paper led by Kevin Stackson, the target selection working group was working out without Gaia data at hand the standard way of finding dwarfs discriminating dwarfs from giants using the so-called reduced proportion diagram. And in situations such as these, you typically end up with a contamination of giants in the dwarf catalog of the order of several tens of percent, 50, 40% or so. This is expected to come down to 0 once they use correctly the Gaia parallax information. We have also heard about the 20 arc-second side of the pictures of TESS. Gaia will tell you down to some level of resolution what's in the neighborhood of your preferred target. This is the probability of finding a binary companions of a given difference in magnitude as a function of separation in arc-seconds. The expectation is that Gaia will be essentially complete to find binary companions up to several magnitudes of difference in brightness, approximately at 1 arc-second. So 20 arc-seconds there. So you should expect to be able to deal with contaminants up to some separation very effectively using Gaia positional information. And then the one thing that everyone has been talking about, the possibility of, for the class of transit systems to determine the planetary parameters, in particular the radius, very accurately using Gaia parallax information. This has already been done. Everyone was expecting to do it. This is a classic example from a recent article by Alessandro, who has done this with a specific purpose of relooking at and redefining what is the gap in planetary radius that identifies objects that appear to be rocky from those that appear to be surrounded by significant gas envelopes. And in doing so, they carry out a redefinition of the uncertainties in the radii of the parent stars, and then, as a consequence, in the radii of the planetary companions that are transiting them. And as you can see, this is pre-Gaia, and this is with Gaia. You see the factor of improvement, which is actually spectacular. And this is something that I wrote as of October last year at a meeting again in Pasadena, less than a year ago. And in fact, you do perfectly confirm the prediction. Gaia parallaxes allow you to really do a spectacular job in terms of redefining stellar and planet parameters. This is much as planet indirect help in the planet field Gaia can give you. Now let's see what Gaia can do with its own data in the planet discovery space. This is a method diagram. I want to just focus you on the planetary mass semi-major axis regime that is accessible by Gaia. The Gaia curves for detection are these in purple. Everything above is detectable with high statistical confidence. And whether it's dotted or whether it's straight line, solid line, is 5 or 10-year mission duration. In the solar neighborhood, around 20 or so parsecs from us, low mass star, or at the distance of the nearest star formation region, Taurus, Forest type. What you bring home in this exercise is that typically, even for stars in the solar neighborhood, Gaia is sensitive to giant planets. And this was, since the beginning, the expectation. Let's also underline this again. Giant planets are interesting and will be interesting as observed by Gaia because they will come in large numbers. And this is the most defining element of legacy for the mission. the sensitivity to planetary companions may be exceeding millions of stars. And this implies, given a recipe for those that are understood to be the frequencies of such objects in the solar neighborhood, the possibility to observe tens of thousands of them. And this number may improve by a large amount, maybe as much as triple, if the mission duration actually gets extended by a factor of 2, and we end up with a 10-year mission. So this is exactly what Gaia will deliver ultimately, a catalog of exoplanetary companions that will be provided by Gaia data editors in the future, will allow you to work out the fine structure of orbital elements of distribution, correlations between planetary frequencies and planetary parameters, and the properties of the parent star, and particularly all the way to the so-called transitions between giant planets and brown dwarfs, because the more massive the companion, the easier for Gaia to say something about its system. This is really the bottom line. And from here, we can go in some detail with a few additional slides. I will go through these very quickly. Correlations and frequencies, as I mentioned. There are known effects of dependence of planetary frequency of giant planets with stellar mass or with stellar metallicity. These seem to be continuously rising function of metallicity or rising functions of stellar mass up to a point. The bottom line is that these graphs you typically use per being in the histogram of order of tens, maybe 100 stars, and what Gaia will allow you to do is do this with at least 100-fold objects in the same bin. In terms of correlations, let's take a look at this very quickly. Do you see a dependence of planetary mass with solar mass? Are more massive objects found more often around more massive stars? That's a hint. Longer period companions found more often around higher solar masses. Primaries, maybe. Other hints. Longer period companions more often found, if you're looking at a transiting class of objects, around more metal-2 stars. Maybe. Longer period companions measured by radio velocity work found typically at longer periods, the more beta-poor the primary is. Maybe. These are two objects that were just recently being rejected of work about to be submitted, and for which there is a poster by Domenico Basso as well in the just outside. We are still in the small number statistics. Can we say something definitive about this? These are all open questions that I am pretty sure Gaia will be able to answer very quantitatively with of order of 10-fold increase in statistical numbers. Then there's the class of young stars. Eric Mauser gave a nice talk yesterday, and he provided this quick summary of known young groups in the neighborhood of the sun. You can expect of order of maybe a couple thousands of young stars available for planet detection with Gaia in the regime of separations of up to several astronomical units. These are going to be typically very massive. They will be maybe closer to the transition region if they are there. But Gaia will be sensitive to these in a regime of separations that is entirely inaccessible as of today to direct imaging devices. There is, however, already now a potentially important element of synergy with direct imaging work. You can, for example, take a look at what is the drift in astrometry residual in milliseconds per year square, the so-called derivative of proper motion, which is an element of of curvature in the data induced by the presence of the companion that Gaia can pick up, indicating the presence of a long period object in the data. These might be also objects that can be, in fact, directly imaged. And in the simulation in the representative sphere GTO target sample of relatively bright stars relatively nearby, this is the location of the curvature effect induced by Epsilon Eridani. This is the sensitivity of Gaia with a 5-year mission, and you can see that the drift in the 7 or 8 astronomical units of separation companion around Epsilon Eridani and many others that could be lurking in the data would be effectively taken. Now let's move across the HR diagram. Here and there we're putting young stars. Let's see post-significant stars. This is the now the matter of revision in ongoing work. White dwarfs will be seen by Gaia in the thousands, most likely. And it might be possible with Gaia to access an element of understanding in the post-planet formation and post-mean sequence planet evolution around the stars that is very hardly done by any other technique. There are, depending on the mass of the companion, predictions on the fact that there should be a gap up to some regimes of orbital separation. So companions should not be there in the post-common envelope evolution of the planetary systems unless they're very massive. And Gaia is expected to provide the defining experiments in this. To conclude, a couple of slides going down to the bottom of the main sequence instead. Ultra-cool dwarf planets. This is now the matter of ongoing research, in particular with the transit technique in the infrared. Brown dwarfs may host planets. We don't know yet. Well, we know one that has popped up in a microlensing event that I know. I don't know if there are others. What I know is that Gaia has the potential to investigate over 1,000 early L dwarfs, typically, so brown dwarfs anyways, nominated masses, of a variety of ages, and it will be sensitive to giant planetary companions, even for these very faint objects. They are all very nearby. They are within 10, 15 parts from the sun, and even with a fraction of milliarc second precision, given that they are so light in mass, the primaries, it will still be possible to access Jupiter mass companions if they're there in the first place. And for the most light system of all, TRAPPIST-1, Gaia can actually do even better. This is a much brighter object than Luan-16 AB, which is already a relevant target because it's a binary brown dwarf, one of the nearest targets to the sun. You can expect to do even better with Gaia data for TRAPPIST-1. I hope that this is going to last. Conclude, Gaia and systems. Systems being binaries. The frequency and orbital elements and mass distribution of planetary systems in binary stellar systems and in around stars that are not known to be in a binary system may or may not differ. Today, historical radio velocity surveys have provided only vague hints of the possibility of differences in these two classes of planetary systems, simply because of the low small number statistics. And a large set of questions that are still up there to be understood do not have a clear answer. And my expectation is that if you can probe over 1 million stars with Gaia, and 50% of these will have a binary companion of a variety of separation, then I'm pretty sure you will be able to do a good job in understanding and providing quantitative answers to these questions. Final, Gaia multiple systems. This is very recent work, a couple of years ago. We started bridging information from direct imaging devices and other velocity spectrometers, and we started learning about the possibility that objects already, systems already known to have a giant planetary companion in the inner regions might be accompanied by additional companions. And the presence of additional companions seems to be a rising function of semi-major axis up to a point and a decreasing function of companionship. So we've done a quick calculation. This is an exercise, nothing published yet, on the possibility of confirming this trend. We are talking here of order of 10 to the 2 systems analyzed for this for the purpose of this analysis. If Gaia can deliver a 10-year mission lifetime, the expectation is that there may be of order of several thousands of 2-planet systems that could be detected. And for some of the, for a fraction of these, maybe of order of 10%, it may even be possible to measure the relative inclination of the optical plane, as it has been nicely seen in the case of the Upsilon system. I think I can close here, and I will not put any summary. I will just give you a word of caution. We have seen our first estimate of the performance of Gaia Astrometry as a function of magnitude, and we have seen that we are still lacking quality in the performance in the bright strategy. All these analyses that are potentially there to be done by Gaia will fundamentally profit by the information that comes for the bright star, because those are the ones that can be measured best. And if Gaia cannot deliver there what is expected, then its impact in the exoplanet field will be primarily statistical, because it will deliver planets that are around very faint primaries, and those will typically not be very amenable for follow-up and additional characterization of the system, and typically will not overlap greatly with all the efforts in transit work, Doppler spectroscopy, atmospheric characterization programs that are focusing primarily on bright stars. So this is the word of caution that I hope will eventually become very pleased confirmation of the fact that Gaia is delivering 2 years from now. That, however, has to be there, because if Gaia cannot do the very best in the bright star regime, its overlap and synergy potential with the rest of the work in the exoplanet field might be significantly hampered. Thank you.
Thank you, Alex. For Ted, his hands up real fast.
Alessandro.
Yes.
So you mentioned extended mission. Is there some intrinsic reason other than money that you would not extend? Are you going to run out of fuel or something?
No, the fuel actually. Yes. So can we be hampered in our efforts to extend the mission by a factor of 2 in lifetime? Is there any reason? Money, fuel. Money is the only one. I hope this is not going to really be the case. Fuel can get Gaia going for another 5 years without problem. And the big trouble that we were expecting in the damage of the detectors induced by the charge transfer inefficiency effect on the heavy ion abundance from the sun has a very limited impact on the lifetime of the detector. So we can go for 10 years, and that's green light. And the science case, particularly for exoplanetary systems, is extremely driving the decision. And I really hope that this is going to fly. Gaia does not give you a green light for 5 years at a time. Sorry, the ESA does not give you a green light 5 years at a time. You have to negotiate 1 to 1.5 year extensions every time, but really, we are really confident. So very quickly, how do we deal with the effect of charge transfer inefficiency?
Sorry, can you repeat the question?
Yeah, that's what I said. How we deal with the effect of charge transfer inefficiency in Gaia detectors. You have seen this distortion effect in the Poisson function. What we've done is to model a priori the effect that comes by injecting artificially charges before the arrival of very bright stars, and that's where the effect is expected to be having most impact. And the distortion that I showed from a standard classical PSS modeling of a normal point source has been, we hope, understood to the extent that when we see them distorted, we have a set of classes of distortions that we know about. We see them and we account it for.
So you give either about Planet 9.
Uh-huh.
And I wonder, while we're at all at Caltech, if you'd like to make any announcements or, really, I just want to know what the sensitivity, has any analysis been done yet, and what sensitivity you expect to have eventually?
With Gaia?
Yeah.
So my expectation is that Gaia is not going to tell you that much about the existence of Planet 9. It will certainly not be able to disentangle the issue of whether the dynamical influence on those trans-Neptunian objects is actually due to the presence of the companion. The population of objects that is potentially affected by the presence of Planet 9 is very faint for Gaia. And while we expect to see some of them, the understanding of the details of the orbital motion will not be really modeled in very great accuracy by Gaia measurement. If we're looking at finding Planet 9 in Gaia data, meaning as a point source, that is out of question. The expectation for okay, so you cannot find it as a point source because it's too faint, much fainter than GE of 20. With astrometric microlensing, the precision of and sampling of Gaia for any source that might be affected is not likely to be deciphered. That's my feeling.
Everyone find him in the break and ask what astrometric microlensing is. All right, that's our time. Let's thank our speakers this morning.